Let us discuss numerical methods of solution of simultaneous algebraic equations. Simultaneous linear algebraic equations occur quite common in various fields of engineering. We had used matrix inversion method or Cramer's rule to solve such equations in general, but these methods become tedious when system of equations consist of large number of unknowns. In order to solve such equations, we have introduced numerical methods which are particularly suitable for computer operations, and these are classified into two categories: directive or iterative. In case of iterative methods, we will have to make use of iterative formulas. Iterative methods are also known as indirect methods. Gauss-Jacobi method, Gauss-Seidel iterative method, and relaxation method are most popular iterative methods. In case of direct method, we do not make use of iterative formulas. Here, amount of computation remains fixed. We have Gauss elimination method, Gauss-Jordan method, triangulation method, Kraut's method are the most popular direct methods. Let us now discuss Gauss elimination method, which is an example for direct method. Let us consider an example. Here in this example, we have been given with three linear equations and we write it in the form Ax equals b, which is the matrix form of linear equations. We have matrix A is known as coefficient matrix, matrix X is known as solution matrix, and matrix B is known as constant matrix. In order to obtain the coefficient matrix A, we will take coefficients of variables of each equations. For example, in the first equation 3x plus y minus z equals 3, the coefficient appearing in the LHS of this equation will be 3, 1, minus 1, which is becoming the first row of coefficient matrix. From the second equation 2x minus 8y plus z equals minus 5, we have the LHS of this equation will give us coefficient of each variable, and we have 2 minus 8, 1 becomes the second row of coefficient matrix. From the third equation x minus 2y plus 9z equals 8, we have from the LHS of this equation coefficient of each variable given by 1 minus 2, 9 becomes the third row of the coefficient matrix. We have x, y, z are the variables appearing common to three equations, and hence column matrix x, y, z becomes the solution matrix. We have B, which is the constant matrix, is obtained by just writing the column matrix involving entries of RHS for each equations given. Here in this method, we will apply row transformations in order to transform coefficient matrix to upper triangular matrix, that is a matrix in which all elements below the principal diagonal or main diagonal will be 0. First step will be to write the augmented matrix. Augmented matrix is nothing but the matrix A slash B, where A is the coefficient matrix and we have an extra column attached to matrix A which is written after the slash, and this matrix will be the constant matrix B. This matrix is known as augmented matrix, represented as A slash B. We have this is the principal diagonal or main diagonal. In order to make coefficient matrix A as upper triangular matrix, we will have to make all these entries which lie below the principal diagonal as zeros. Whichever transformations we apply, it is applicable to these entries as well. If you consider the row transformation, R2 changes to R2 minus 2 by 3 times R1, we have row 1 of augmented matrix remains unchanged. Row 2 will be changed such that we will have new entries. 2 changes to 2 minus 2 by 3 times 3, which becomes 0 here. For this value, we will have minus 8 changes such that minus 8 minus 2 by 3 times 1, which becomes minus 8 minus 2 by 3, which becomes minus 26 by 3, which is written here. For obtaining this value, we will have 1 changes to 1 minus 2 by 3 times negative 1, which becomes 1 plus 2 by 3, which becomes 5 by 3, and this value is written here. Now we have made this entry as 0 here. Next step will be to make this entry as 0. For that, we can make use of the row transformation. R3 changes such that R3 minus 1 by 3 times R1. Notice that when this row transformation is applied on this value of the constant matrix, we have minus 5 changes such that minus 5 minus 2 by 3 times 3. Thus we have minus 5 minus 2 by 3 multiplied to 3 becoming minus 7, which is updated value written here. When we apply the new row transformation, we will have 1 changes to 1 minus 1 by 3 times 3. Thus we have 0 obtained here. Similarly, we have minus 2 changes such that minus 2 minus 1 by 3 times 1, which will give us minus 7 by 3. 9 changes such that 9 minus 1 by 3 times minus 1, which becomes 28 by 3. We obtained minus 7 by 3 here by minus 2 minus 1 by 3, and we obtained 28 by 3 here by 9 plus 1 by 3. Similarly, for this value, the change will be that 8 minus 1 by 3 times 3, which will give us 7, which is written here. In the next step, we will use transformation such that this value can be changed to 0. If we apply the row transformation, R3 changes such that R3 minus 7 by 26 times R2, we will have this entry changed such that minus 7 by 3 minus 7 by 26 times minus 26 by 3, which makes this entry 0. When you apply the same row transformation for these two positions, we will have this position changed such that 28 by 3 minus 7 by 26 times 5 by 3, which will give us 693 divided by 78 in this position. Here for the constant matrix, applying the row transformation, we will obtain 7 minus 7 by 26 times minus 7, which will give us 231 divided by 26. Thus, applying this row transformation, we have obtained augmented matrix updated in this way. Now, since our coefficient matrix is in upper triangular format, we can have the matrix form rewritten as Ax equals B, becoming this coefficient matrix A into solution matrix equals this constant matrix, which is B.